Welcome everyone to the October 2021 indoor meeting. Please be respectful and mute your mics during the presentation. And welcome the first-time guests as well as new club members. We want to remind you, if you joined the Raleigh Astronomy Club during the fourth quarter of the year, which we're in now, your entire next year membership will be included. So if you're interested in joining the Raleigh Astronomy Club, you can reach out to any of us officers or leadership group, or you can go on the website and find how to join there. Our presentation tonight is on the James Webb Space Telescope. The James Webb Space Telescope is the largest, most powerful space telescope ever built. Webb will gaze into the epoch when the very first stars and galaxies formed over 13.5 billion years ago. Its revolutionary technology will study every phase of cosmic history, from within our solar system to the most distant observable galaxies in the early universe. Webb's infrared telescope will explore a wide range of science questions to help us understand the origins of the universe and our place in it. So to help us learn more about the James Webb Space Telescope is our speaker, Dr. Nikolay Nikolov. He is an astronomer at the Space Telescope Science Institute in Baltimore, Maryland. He's an instrument scientist responsible for Webb's NIRCam and primarily studies the makeup of planets orbiting other stars and how they may have been born. In his work, he makes use of NASA's greatest observatories, including the Hubble Space Telescope and the soon-to-be-launched James Webb Space Telescope. Nikolay became excited about science and astronomy when he was a student in his home country of Bulgaria. When he saw beautiful images of planets, stars, and galaxies taken with the Hubble Space Telescope, he fell in love with astronomy. Nikolay followed his dream of becoming an astronomer and has both studied and worked in Germany, England, and here in the US. So without further ado, I will hand it over to Nikolay.
Thank you, Anastasia, and thanks everyone for having me at your Astro Club to give this talk. Just before I start, can everyone see my first slide? Yeah, okay, perfect. So as you, Anastasia, said, I'm going to talk about our new infrared eyes on the universe, which will be brought in space by the exciting James Webb Space Telescope. So this is actually the biggest and the most advanced observatory humanity ever built, and is going to unleash a lot of secrets of the universe and help us understand more about the universe and about our place in it. So let's first talk about how Webb came to be. Why did we build the James Webb Space Telescope? And actually, nothing starts as of today. We have a history of building observatories in the past. Specifically, NASA has experienced launching telescopes since the 1990s, when most of you might remember that the Hobo Space Telescope was brought into space and advancing our understanding of many aspects of the universe, starting from the solar system, planets, to stars, star formation, galaxies, and the expansion of the universe. So that was back in 1990s. But then this observatory was followed up by other exciting observatories such as Chandra, which launched in 1999 and is still operational, focusing on X-ray light. Then we also had the Spitzer Space Telescope, which was built and launched around 2003 and was in operation by last year. So the Spitzer Space Telescope was also in infrared light. So basically, the three observatories that NASA has built, launched, and used to extend our knowledge about the universe are actually very highly complementary. They don't look at the same light, but rather help us look through different windows toward the universe. And by combining this information, we can have a more thorough and more in-depth picture of what is going on in the universe. But why, before everything, do we need to put telescopes in space? Well, I suppose many of you might know the answer because, for example, when you observe above the Earth atmosphere, you no longer need to care about day and night. You don't need to care about this blurring that our own atmosphere is causing to the images. So that means that if you want to have a really detailed image of a galaxy, for example, and you would like to learn the details on its morphology, on its structure, introducing a telescope in space would actually be very beneficial, as it provides crisp images. In addition to this blurring effect that the Earth atmosphere does, it also filters some of the light. That means that part of the light is completely lost before it reaches us. And that's very unfortunate, as most of the light, for instance, of all galaxies has traveled so long to reach to our eyes, but we lose it just in its final steps of its trip. So putting telescopes in space actually helps us avoid this obstacle. So what have we learned with the Hubble Space Telescope, for example? Well, here is a snapshot of 4 very important images that reveal different objects, which I'm going to look into detail in a second. With the Hubble Space Telescope, with Spitzer Space Telescope, and with Chandra. So by combining the light of those 3 very exciting and great observatories, we learned many different aspects. For example, if we focus on the first image on the top left corner, this is the very well-known Crab Nebula. This nebula, actually, before it becomes a nebula, has been observed in 1054 AD as a very bright star. At the time, of course, nobody knew what exactly it is, but nowadays, with NASA's great observatories, we have been able to look into detail with the Hubble Space Telescope and with Chandra, for instance. And now we know that this is a remnant of an exploding star. And we've learned, for example, the structure of the gas around this star, how it moves, which helps us better understand about this stage of the life of stars. On the next image, this is Zeta Ophiuchi. This is a star which is inside a nebula. And basically, by combining different light from observed with different observatories, we actually observed that the gas around this star actually exhibits ripples very similar to the ripples, for example, of a boat moving in a lake or a river. So that tells us, for example, where such stars are born, how they evolve, and how they die. Then on the lower left corner, you have the very famous to every amateur astrophotographer Ring Nebula, which from the ground, for example, if you image it, even with the most advanced technique or instrumentation available to amateur astronomers, you won't be able to see much detail. But by putting a telescope in space and by looking at different lights, for example, visible light or infrared light, for which I will talk more in detail in a minute, you can actually see a lot of details there and study the gas that is around this basically dying star, the bright star in the middle of the image. Also, by combining information, observations from these 3 NASA great observatories, Hubble, Spitzer, and Chandra, if you look into galaxies which interact with each other, just like the galaxies on the image shown on the lower right, which are the antenna galaxies, these are actually 2 galaxies which are just by chance captured in a big dance. So not all the galaxies in the universe form and exist in isolation. Some of them, actually many of them, tend to go very close to each other and distort their shape over very long time periods, and they change their shape to very, wandering shapes. And for example, this picture here shows 2 galaxies in a stage of interaction with each other. But by combining different lights, you can actually study different aspects of these galaxies. For example, with Hubble, if you look at visible light, you can see the big picture of these galaxies. But if you look with Chandra at X-rays, you can see some of the brightest and the hottest objects, which are shown here in red. The Hubble image is shown in gold and brown, and the infrared light from the Spitzer Space Telescope is actually shown in blue. So by looking at different light, you see different parts of objects and you learn different things. So the four images that I was showing are only some of the brightest, and some of them are even some of the closest to our solar system. But what about the deep space? What about the most distant objects, those that have formed nearly at the beginning of the formation of the universe after the Big Bang? Well, as some of you may know, back in 1995, Hobo pointed at what looked to be a completely empty patch on the sky, a completely empty part of the night sky, and it collected images for a very long exposure, so that when you combine all the data, you would see really faint objects. That's the so-called deep Hubble deep field. In this slide here, I'm showing not the 1995 one, but a newer in 2014. And by looking at very empty portions of the night sky for a long time, you can actually collect light and build image of what the universe must have looked many years ago. Now, if we can do this with only around 2.5 meter telescope, think about what it could be if you observe with a 6 meter telescope in space. That's one of the biggest adventures that James Webb is going to offer us. Basically, look at some of the first galaxies formed in the universe. But before we go into detail about James Webb, why do we need to look at infrared light, and what is actually infrared light? How is it important to us? Well, in the next slides, I'm going to say a few words about it. You all know that we currently in science, we consider that the universe has started following a big explosion known as the Big Bang, when the universe was very dense and very homogenized, which started to expand over time. And actually, if you want to observe at those very early stages of the universe, you won't be able to do that in visible light. That means the light that we perceive with our own eyes. Why is that? Well, the idea is that when the universe was very early in its evolution, when it formed, it was so hot that the light was actually very energetic. So that means it was nearly X-ray or even gamma ray. But what happens as the universe expands? As the universe expands, actually, that light stretches. And if you imagine that the light as is represented as a wave, as we think it is, this wave also stretches as the universe expands. And nowadays, the light from the first galaxies has stretched so much during the duration from the Big Bang to the present days that it actually is no longer X-ray. It actually is in the much less energetic wavelengths, which are known as infrared light, or we know it simply as heat. So let's see some of the important and critical aspects about the James Webb Space Telescope. How does it look if we want to collect infrared light, and what characteristics it has? Well, first of all, here on the left picture, I'm showing just a cartoon of how James Webb looks, and compared to known objects, just to have an idea about the scale. And on the right-hand side, I'm showing a full 360 view around the telescope and how it looks. James Webb is big. It's actually very big. It is as long as a tennis court, and it is as tall as a 3-story building. So you can imagine that we haven't built a bigger observatory, and we haven't put such thing in space so far. So it's going to be a great achievement when we do this for the first time, and it will open the future for actually considering even building bigger telescopes. With the current, for example, observatories on the ground, the Keck Observatory has around 10-meter telescope mirror, and the Grand Tecan telescope, which is on the Canary Islands opposite to Africa, we have similar observatory, and those are our biggest on the ground. So putting a 6-meter class telescope in space is actually not much smaller in size. So it's really remarkable. And how is this going to be brought into space so big? Well, James Webb actually has been built in such a way that you can fold it as an umbrella, fit it into a rocket, and as the rocket launches and departs the atmosphere of Earth, it will start unfolding slowly in its important parts. Actually, here is one of the very critical things to mention. There are so many critical points of failure where the mission could have issues that when the telescope was built, it had to undergo very detailed and thorough testing to make sure that we don't have none of those critical points failed, so that the observatory is success. Okay, we learned about the size of the observatory, but what about this infrared light or the heat, and why do we need to look in that in much detail if we already had 3 observatories with some of them looking at infrared? Well, the infrared light actually turns out to be very important when we want to glean information about the universe. Here is an example of some of the everyday experience of firefighters, for instance. On the left-hand side, you have a visible light image of a fire scene where you could only see one firefighter and some smoke in that room. But on the right-hand side, you have the same image, but imaged with an infrared camera. And you can immediately see what is the big difference here. Basically, if you look at visible light, the only thing you can see is only this smoke. And you can't say much about what is in that room. You remember that compared to firefighters, astronomers cannot go into the scenes they study. They can study them only from apart, only from very far away from them, and analyze what they see with their own eyes. So if you switch to infrared light, it's striking how the room becomes transparent. So you can see now on the right-hand side, basically even a person laying on the ground, and such cameras actually are important as they can save life in firefighters' everyday fire scenes. So in a similar way, the infrared cameras on the James Webb Space Telescope are going to look on the sky at a different light. For instance, if we go back and revisit some of the known objects, like, for instance, the Eagle Nebula shown here in 3 distinct images, the first one in visible light obtained with the Hubble Space Telescope, and the second in near-infrared light, or a little bit of heat, so to speak, again with the Hubble Space Telescope and its infrared capability, you can see totally different picture. And then in the third one is mid-infrared light, what we have seen here, what we expect to see with JWST. So you can see that on the 3 scenes, there are different objects visible. On the visible light, you can see the big picture and some of the stars, some of the so-called pillars of creation, or these are big complex structures of a gas from which stars are born, are considered to be born, and they are shredded by this gas and invisible when you look at optical or visible light. If you look at the near-infrared light, well, it becomes a little bit more transparent. Now you can see much more stars just because the gas on the first image now becomes transparent. And you can see some of the stars which have been shredded by cocoons of gas from which they form. And with JWST, we will be able to even see in more detail at mid-infrared light, where we will see basically the clusters of stars which are just forming. So one important aspect to mention here is that while with the current technology, we can't see at every at many infrared wavelengths or at many different infrared colors in crisp detail or very clean images, just like Hobo. With JWST, that will be possible. So we will see images which are similar to the visible light image shown here on the left, but in infrared light. Okay, so in order to have an observatory that works in infrared light, we actually need to secure the observatory to operate for that wavelength region. That's one of the reasons actually why this new observatory has a big shield, or we can call it just hat, but basically this is a sunscreen, a protection from the glare of the sun, as well as from heating the observatories. In order to work at infrared light, the observatory needs to cool to very low temperature, and JWST is actually using passive cooling method. And the passive cooling method relies on several membranes, which are shown here as this big rhomboid features, which are extended when the observatory unfolds after following its launch, and they will basically secure that the dark side on which the observatory mirror is located is going to reach the necessary low temperatures. And also to make sure that the observatory can effectively collect infrared light, its mirror won't work that efficient if it is like a conventional aluminum coated mirror. Actually, from scientific reasons, we found that if you cover the mirror with gold, it would work much better. And so another fun fact for this observatory is that its primary mirror is covered with gold. Okay, let's look more what we are going to learn with the JWST. I already mentioned that one of the prime ideas for launching JWST is to look very distant objects, some of the first galaxies that were born. And so here I'm showing 4 cartoons. On the first one, you can see these 4 cartoons are showing the very schematically the formation of the universe at the beginning, the formation of the galaxies in the universe at the beginning. So basically, following the Big Bang, on the left-hand side, you have at the beginning the universe is a very different place compared to what is today. It's actually very dense. Not much light can travel through it, and some of the first stars start to form. Then you have some of those stars starting to assemble together and to form some of the first galaxies. Then the galaxies become more visible, then more and more matter is attracted, and the universe basically clears and light can travel in the universe. So in order to see so distant object, and at the beginning, following the reionization, this stage is called reionization of the universe, you actually need to look at infrared light, again, because of the reason that the universe expands and this initial, basically very energetic light becomes more low energetic or infrared or heat. Here is an example of actually what happens if you imagine that where the Earth is compared to those galaxies on the right-hand side, basically as the universe expands, light also stretches out to lower and less energetic wavelengths, which wave is going to detect. And we have evidence to think that some of the first galaxies did not look to anything that we know today. For example, most of the galaxies, as we know, they look either like spirals or like ellipsoids or spheres. But actually, we don't really know how exactly the earliest galaxies look like. So with Webb, we will be able to stare at some of those very distant objects and learn about their morphology. In addition to that, Webb will actually also help us learn about how these galaxies evolve. So by observing galaxies at different distances, we can actually do in a statistical way study what is the morphology of these galaxies. For example, if we have a different redshifts, many observations of many different galaxies, we can systematize them and we can understand how they look. For example, with the Hubble Space Telescope, we have started to do such analysis, and we know that the older, the younger the galaxies are, or the closer to the Big Bang galaxies are, they are less and less structured. They look more and more simple. And with Webb, it will be possible to actually learn in more detail about galaxy evolution. Some of you may know that we have evidence that in the center of the Milky Way, there is a massive black hole. Now, how did we learn about the existence of this massive black hole if black holes can't be directly observed? Well, you can't observe the black hole directly, but what you can do is you can study the objects, including gas or stars that move in the vicinity of a suspected object to be a black hole. And if these objects are moving, you can actually analyze how they exactly move over time. It typically takes many years to do that. You can't do it for one night or a couple of months. But basically, by studying how the nearby objects in the vicinity of a suspected black hole move, you can actually measure the mass that causes those objects to move, and measure the mass of the suspected object to be a black hole. Actually, this is how we find out that in the center of our galaxy, the Milky Way, the mass of an object that would cause the motion of stars around it in the way we see it with Hubble and other observatories correspond to a very big mass that is only possible for an object that has become a black hole. In a similar way, we hope to use the James Webb Space Telescope to look into the centers of other nearby galaxies, for example, Andromeda, M33, or many others, and study in detail the vicinity of their centers with the goal to show or to learn what exists there. We will go back and re-examine again star formation regions. With James Webb Space Telescope, it will be possible to look in much better, in much finer detail how stars are formed. the planets are the next one. So with JWST, we will be also able to study objects inside our solar system. For example, all the planets that are more distant than Mars, including, we will be able to look into their atmospheres and study how the gas moves, what are the weather patterns in their atmospheres, and we will complement that with observations that we have done already with ground-based observatories or with some of the satellites and probes that we have sent to some of those planets. But we now know that planets don't exist only in our solar system. We know that planets do exist around stars in our galaxies. In fact, over the last 20 years, we learned that nearly every second star that we see on the sky potentially has a planet, and some of them potentially have more than one planet. For example, here on this animation, I'm showing a star whose light actually has been blocked by a coronagraph. Some of you may know, but for everyone, I would mention that coronagraphs are such devices which allow us to block the light from stars and actually look very close in the vicinity of such star with the goal to detect light from objects that move around it. In this example here, I'm showing the system around HR, I think 877. Forgive me if I don't have the exact number, but this system is one of our best examples of directly image similar to our solar system, extrasolar system. With Webb, we will be able not only to detect such systems, but to actually analyze the light that comes from such stars in detail and learn what is the composition of the atmospheres of such planets. Now, these are typically gas giant planets. So those are Jupiter-like planets moving around these stars. But we hope also to look into the atmospheres of Earth-like planets. For example, here I'm showing one such so-called spectrum, or how the light would look at individual colors if we see into the atmosphere of an Earth-like planet. In fact, this is the spectrum of our own Earth atmosphere. And you can see that it's full of peaks and troughs, and actually all these peaks correspond to specific elements which we have learned in detail by just studying them in laboratory conditions and then looking and identifying them into the spectra of known objects, such as the spectrum of the Earth atmosphere. And here you can see it's full of oxygen, water, carbon dioxide, methane. So in a similar way, planets that orbit other stars will be studied in detail with the James Webb Space Telescope. By looking into such planets which are not visible directly, not like the directly imaged planet that I showed in the previous slide. For many of the known exoplanets or extrasolar planets, we know that they periodically pass in front the stars and block part of the starlight. So now that is great, but actually when the planet blocks part of the starlight, that starlight also filters through the planetary atmosphere, and this is how the spectrum of the planet is formed. And depending on the composition of the planet, you have different peaks. So if you identify the individual peaks, you can actually learn what is the composition of the atmosphere of that planet without the need going there. We hope with James Webb Space Telescope, it will be possible to do this kind of analysis routinely for Earth-like planets, and we really hope that it will be possible for some of them to even look for signatures that we believe are relevant to the existence of life. That's really incredible opportunity, if you think of, because for so long humanity has been around, but it's exactly our generation that will be able to see this for the first time. This is incredible. I don't know how much time more I have, but that's what I really wanted to speak during this talk. If you are comfortable with the time, I can continue and speak more about James Webb, or we can just leave it here, and I would be glad to have your questions.
Well, let's see. Mike, did we have any questions on Facebook at all?
I haven't seen any questions on Facebook, but definitely love to hear more about the actual scope. But
Yeah,
we can go another 15, 20 minutes.
Ah, okay,
Yep.
perfect. So here I would like to show you just a more real scale about the size of the observatory and how it really looks at when it was built. So you can see here a comparison between the size of the telescope mirror compared to a human, and it's really big. So the design of the observatory is completely driven by the scientific purpose. So if you want to observe at infrared light, you need to optimize every aspect. So that's the reason behind the gold mirror. That's the reason behind these shields that you can see extended here on the lower right corner. Yeah, we are making a really huge leap compared to Hubble. So Hubble, which was launched in the beginning of the 90s, it is only 2.4 meter. This one is 6 meter, and you can see the big difference. Maybe you may ask why the mirror is segmented instead of a monolithic mirror. And the reason is actually experience and need. Why the experience? Well, in the 90s, when Hubble was launched, we had the problem with the shape of the mirror in space, which caused, I think, spherical aberration. That means the images were blurred compared to the crispness they needed to reach, and it required an additional optical element to be designed to correct for that. I don't want to go into detail about the reasons why the mirror wasn't accounted for the shape on the surface of the ground and in space. But basically, if you build a mirror with segments, you can have control on the actual shape of each segment. And so if you combine all these hexagonal mirrors into one big 6 meter mirror with the option to correct the surface of each segment, if you have any issues, you will be in position to actually apply those corrections and make sure that the shape really reaches the requirements that are necessary for a 6 meter telescope without the need to service the telescope on site. So that means without the need to go there, because compared to Hubble, Webb is going to be much further from us to allow easy service with astronauts. Hubble is on a low orbit. It's only 500 kilometers, about 500 to 600 kilometers. So it was conveniently done. I mean, servicing used to be conveniently done, not anymore, of course, but hopefully we will have it again soon. So here I would like to show you where the observatory is supposed to be. So you have the sun and the earth and the moon. So while Hubble orbits very close to the surface of the earth, Webb is going to be actually beyond the sun-moon system. And this shield is going to be all the time pointing toward the sun with its surface area, while the mirror is going to be pointing in the opposite direction, and it will travel with the earth. So that means we will have constantly changing pattern on the sky. Of course, we will have also continuous viewing zone. That means a zone that the observatory can observe at all times, but it's going to be very limited. Here is a more closer look at the observatory in these two panels. You can see, basically, you can code them code site, which is basically the mirror with the support, the diagonal or the secondary mirror, and you have the hot part, which is on the right-hand side. This is the part that faces the sun. And you can identify as some of the famous telescope parts. Basically, you have the primary mirror, the secondary mirror, you have the science instruments attached toward the back of the primary mirror. You have this multi-layer sun shield, and then on the hot part you have solar power array, the communication antenna, star trackers, and so on. And with regards to the launch, here you can see a sequence of what we expect to happen following the launch. So you can see initially the observatory is going to be folded just like an umbrella, and then over a period of 2 weeks it's going to unfold slowly and meticulously until it basically fully unfolds and is ready for calibration and testing of all the observing modes that we can use on this observatory. So it is really one of the biggest challenges to build such big telescope, but also to pack it such that it resists all the shaking, all the vibrations, and all the risks that you can have when you basically launch and transport such precious luggage, so to speak, beyond the surface of the Earth into a rocket. It's a very precise technology that needs to be protected until it reaches its site for operations. Here I wanted to mention that the way we will communicate with the observatory is via the Deep Space Network in Goldstone, California. This is a big radio antenna that will communicate with the JWST, and the science operations are going to happen in Baltimore, Maryland at the Space Telescope Science Institute where I work. There we will be doing basically preparation and execution of operations, calibrations, and reduction of the data and delivery of the data to the general science community. There will be use via the MAST archive. All the data will be available there, not only for professional astronomers. Actually, amateur astronomers can also go there, download data, and if they want to work on image analysis, they don't need to start from scratch. They will already have reduced images, just like we have today for many of the Hubble Space Telescope images. And here it's important to mention that actually some of the science programs are looking at star formation, for example, which is no different than what an amateur astronomer would do with wide field astrophotography, for example. So the telescope will collect detailed images of individual portions of a big scene, which is then built together by matching the individual images, just like when we do a puzzle scene. And you can actually go and obtain this kind of data even today for Hobo, and you will be able to do it for JWST. Here I wanted to show that actually the observatory is a collaboration between the United States and Europe. So many countries from Western Europe are involved and are leading some of the science instruments. For example, we have 4 major instruments, and 2 are led from European-based astronomers and institutions. One is led here in the US, and another one is a collaborative effort between US and other partners. So it's really an international collaboration built from scientists and engineers for science, basically for humanity. Everyone can use the data, and astronomers and scientists will be the ones that will help interpret what we see, but the data is open to everyone. And that's basically what I have to say you tonight, and would be really glad if you have some questions. I hope to be able to address all of them. Thank you so much for your patience and attention.
Thank you so much, Nikolay. Yeah, we do have some questions in the chat. So it looks like the first one was already answered. Had a couple people ask when the launch was. It's slated for later this year. I believe the estimated date is December 18th, as Mike said.
Yeah.
Doug asked, how does the ablative shield act as a passive cooler? Does it cool the telescope enough that it will not need to carry liquefied gas to keep it cold?
Yeah, so the shield is only doing part of the job. There will be cryogen because infrared detectors, especially at those wavelengths, work at very low temperature. And I think the cryogen, this is the cooling liquid, is going to work for some amount of time, and then when it's over, the observatory will continue working only on the passive cooling shield. So basically, it will increase the temperatures a little bit, but it will still allow us to do science. We may lose some of the longest wavelengths, so to speak, but still for significant part of the remaining wavelengths, we will be able to do operations.
Awesome. And so Mike asked, will each segment have actuators?
I think so, yes. Each segment has actuators. They are built on different panels, but in order to have full control, actuators are on every segment, so that, yeah, there are tests, for instance, where you have to adjust all of them very precisely to have the full capability attained. So every panel and every segment can be controlled separately.
Awesome, thanks. And so Steve asked, does the sun shield move relative to the mirror? If not, then I guess that really impacts where the mirror can be pointed at any particular time.
So my understanding is that the shield is always pointing toward the sun, and then the mirror can move up and down. And you can also a little bit tilt the shield too, so that you have much wider field of view. And as we move around the sun, you can see different parts of the night sky, of the sky. Yeah, you don't have night sky in space, right? It's sky all the time. It's night all the time, except if you look at the sun.
All right, and so Barton asks, how do you deal with objects of different sizes or fields of view?
I guess, if I understand correctly, the question, how would we image a field of view that is very bigger than the field of view of the telescope? In that case, you do dithering. You make a mosaic image. You build individual pieces and then combine them to get the big picture. You can't really, on ground-based observatories, you can really change optical elements mounted in the secondary mirror, or depending on the system of the telescope, and you can have wider field or shorter. It depends what you do. For example, this observatory has many capabilities. It has basically imaging, it has spectroscopy, it has coronagraphy. So combining all this in an automatic way and allowing switch between different observing modes is really challenging, but it has been done. So for instance, if you want to look at an exoplanet, you would switch to coronagraphy, in that case, you block the star light and you look in the vicinity of the star. So the field of view is really small. But say if you want to make an image of a galaxy cluster or say a big star forming region, then you will switch to some imaging camera like the NIRCam camera, which has the biggest detectors on the observatory. And if you do dithering again, you can combine then the individual dithers into a big scene and study many objects. But say if you want to take only small part of the sky, like a small galaxy, you could probably switch to some of the smaller imagers, for example, to NIRIS or NIRSpec, and basically look at smaller images. Then for spectra is the same thing. If you want a spectrum of a star, you switch to NIRSpec, and NIRSpec will give you different spectral resolution. You have many different resolutions. You can look at the entire, say, wavelength range from, I don't know, 0.8 microns to around 2-3 microns, or from around 4 micron to 10 micron if you use MIRI, and you can only collect spectra, for example. You can observe exoplanets as they transit in front of their stars by collecting spectra, say, every 0.2 seconds, and have thousands of spectra and analyze them. So a lot of opportunities, actually. It's a very versatile observatory and can see in pretty much everything that you can imagine.
Awesome, thanks. And so Doug also asked, how long will it take to achieve orbit at L2?
I think the travel to the orbit is around 2 weeks, and this is a time during the observatory will unfold, but then there will be maneuvers to stabilize the observatory, do the alignments and everything. So I would say the first 6 months following the launch are going to be exactly to prepare the observatory and make it ready for science observation. So yeah, the exact travel time you can assume around 2 weeks, but really when the observatory will be ready, I would say 6 months following the launch.
All right, and so Mike says, what is the expected working lifetime of JWST?
Sorry, could you repeat the question? What is the expected?
What is the expected working lifetime of JWST?
The expecting lifetime. So we hope that we will, so I think the cryogen is going to last for between 5 and 7 or even 8 years. And beyond that, I think the observatory, how long it's going to stay, would depend pretty much on the state it is. Basically what functions and whether there are some issues or not, but its actual lifetime can be much longer than that. I mean, you can see with Hobo, it has been launched in what, 1990, 1991, and it's still there, and we still hope to have it around. So the big difference is that it doesn't operate at mid-infrared, and so you don't rely very much on cryogen to cool the instrumentation. But with Webb, you will have wavelengths which won't require cryogen, so it should be there for a long time.
And Doug asked, will the sun try to push the telescope out of its orbit at L2?
Yes, I suppose so. There are physical mechanisms for that, which, for example, we see on comets and asteroids. With this big shield, of course, you can imagine that the solar radiation and wind is going to exercise some pressure. But I think the observatory is also equipped with some thrusters which can make small corrections. And I can't tell you exactly how much fuel we will have, but I'm sure that it has been taken into account to do such corrections if needed. I mean, to counteract the wind from the sun.
And then so we also have, what is the effective resolution in arc seconds?
Oh, I can't tell you the exact number. I personally work as a scientist on spectroscopy. So if you ask me about spectral resolution, I can tell you, but I'm not very good telling you about the actual resolution in ArcSec. I never actually care about this. Sorry about that. I can check and let you know if you let me know for your name or email address and get back to you, but it's not on the top of my head right now. I imagine it's a factor of, I don't know, 2-digit number of improvement compared to, say, ground-based observatories or even HST.
All right, and then from Colin, he asks, what will be the next space telescope after JWST? Is
Oh,
something
that's
currently in the planning stage?
That's my favorite question. So basically, with a 6-meter class telescope in space, we have started thinking about many even more challenging projects. For example, my favorite project is called it has many different names. Okay, maybe it's not the greatest idea to talk about the exact name because it will change. Basically, the concept would be to launch similar observatory with larger aperture, larger mirror, and launch also a shade, big shade that you place it many miles in front of the observatory. And by coordinating, again, with these thrusters, the position of the shade in front of the observatory,
the wine aerator
you will be able to look,
rubber ring, right?
you would be able to look again, just like what we do for coronagraphy, in the vicinity of stars with planets and study their atmospheres. Basically, it will again be an infrared, mid-infrared observatory, and you would look in the atmospheres of those planets and see what molecules and atoms you can identify their signatures and basically learn about the composition of the atmospheres of such planets. And so if you remember the spectrum that I showed of the Earth atmosphere, with such observatories, we will be able to do in a statistical way study of many Earth-like planets and the composition of their atmospheres. And eventually in some of them, we hope to find evidence for gases that have been produced by living organisms. That would tell us, for example, how common life is in the universe, something that we only imagine might have been in the universe, but we haven't found evidence for it. Other observatories, actually, this is kind of a mid-30s and onward idea, but on the shorter time scale, there is the Nancy Gray Roman telescope, I think, which is now in preparation, and it's going to look in a very large part of the sky and study planets that transit around other stars. Actually, those are planets which are going to be targeted with the concept of big telescope in space with a shade one day. What else? We also have other observatories coming. At the moment, actually, we have TESS that is looking for planets, but is going to be followed up by other space observatories also finding planets and learning their atmospheres. That's actually one of the biggest motivations for sending telescopes in space, we think, today.
Awesome, thanks. And so let's see, Dick White asks, any chances for enhancements or repairs during its working life?
Who knows? Probably, likely, why not? We can see now the development of private companies with regards to space business. Maybe one day it may be possible to even send again servicing missions to HST. Hopefully SpaceX is not going to destroy HST because they seem to be on similar orbits. But if it survives, why not? Webb is going to be very far. So you can imagine that the risk of sending people there would be quite big. So I could imagine a robotic mission one day, but I can't say when. Definitely, it's not going to be in the next 5 or 10 years, probably, but maybe at that time, plus 5 years, it might be possible.
Sure, yeah. And then we have Matt, who loves spectroscopy. He excitedly asks, what is the spectral resolution over what wavelengths?
So Webb has many different spectral resolutions. For example, you can go as low as spectral resolution of 100 to spectral resolution of around 5,000. So you just need to switch between different spectrometers. For example, NIRSpec and NIRCam have the highest resolution, but on the other hand, if you go to NIRIS, it has the lowest resolution. And so the big advantages of having low and high resolution are the following. If you look at low resolution, say if you study an exoplanet atmosphere, with the low resolution spectrograph, you can get the entire spectrum in one shot, basically in one observation. But if you spot something suspicious, and by suspicious, I mean in the good way, like absorption signature or emission signature, a line, you can then switch to higher spectral resolution, the highest of JWST. And you can go back in a new observation and you can study the profile, you can study how this looks, and basically the shape, the peak can tell you about the physical conditions of the material that you are looking at. Could be gas, dust, I don't know.
Awesome, thanks. And then Jordan asks, what is the confidence level of a launch in December? It was originally supposed to launch like Halloween, right?
Yes, I can't tell you, but I can't tell you because I don't know. But when the date slips, basically, okay, the key is in the step of the slip. If the slip is months, that means, okay, maybe there's going to be another couple of months, maybe there will be another couple of months. But if it is weeks, it's likely that it will become days. So that means we are closer and closer and closer, and it won't happen that we will have to delay with 6 months or a year.
Yeah, I think now it's really the fact that it's now at, down in Guyana. I think it's now just a question of really, it's not necessarily this telescope, it's the hardware, the rocket, or the weather at this point.
Yeah, we wait for the taxi to come and pick up the luggage and send it to its destination, unless weather worsens, as you say, or unless something technical occurs, but it won't be relevant to the science instruments because they have been tested, they are, stamped, ready to go, and it has to be something completely different outside of the observatory, something with the rocket or some other reason. So whatever was needed to be completed by the engineers and the people that test the observatory, it has been done already. Otherwise, it wouldn't be shipped and in French Guiana right now.
All right, awesome. Does anybody else have any questions for Nikolay? I don't see any more in the chat, but I wanted to give every opportunity to chime in if they have one.
Yeah, I just wanted to make a comment on, I guess, Dick White's question. So with, I think L2 is about 1 million miles away from Earth. So when you think about the moon being only 240,000 miles, that's as far as humans have ever gone. We would need to extend, easily, 4 times the, whatever spacecraft we would have in the future, to be able to make that sort of trip and stay there. So a human mission out to L2 for a repair, probably not anything with the current spacecraft that we have.
Yeah, I agree. And if something happens, you can't react quickly. So if we had, say, I don't know, yeah, maybe it's too many movies that I've watched, but if you had individual stations, so to speak, where they can help each other, then the risk is not so high. But packing and sending people for a long time, it's actually out of question, I think. So it's going to be some robotized mission or something.
Yep. Or we can send Captain Kirk as Jordan comment.
All right, does anybody else have any questions or comments for Nikolay?
Did not see any questions or posts on Facebook.
Okay, awesome. All right, well, thank you so much again, Nikolay, for being here and presenting on James Webb Space Telescope. It was an awesome presentation. We all really very much enjoyed it, and we really appreciate your time coming in and presenting to us.
Thank you
And
so
so-
much.
Here, here.
And
Thank you. It was wonderful.
Thank you, thank you. And feel free to reach me via Anastasia. My email is probably available there. So if you have any questions, just feel free to drop me an email. I'll be glad to respond. I also started actually my career as an amateur astronomer. When I was a high school student, we actually established an astro club. Astrophotography was the reason that it was the thing that got me in astronomy back in the end of the 90s, when I was using only, you know, photographic plates to do this with not much of a, you know, technology.
Wow.
So I'm really glad to speak to people that are driven by the same in an astro club. I really miss my astro club in Bulgaria. Anyway, that's another 1 hour.
well, you're welcome to join any of our meetings anytime. I'm sure I can speak for anybody on
Thank you.
that.
Definitely.